Today, we explore the critical transition of power networks from legacy copper based systems to high speed digital automation. This transformation brings immense efficiency but introduces complex security challenges. Our training roadmap is built on six foundational pillars. We start with smart grid architecture, then dive into IEC 61850 communication for high speed protection and the sampled values protocol. Next, we map out the global SCADA protocols like DNP3 and IEC 104. Finally, we address cybersecurity, detailing mandatory NERSC CIP standards and implementing zero trust architecture for OT networks. To understand the modern digital grid, we must start at its foundation, the edge layer, where power meets the consumer. This is the domain of Advanced Metering Infrastructure, or AMI. Unlike legacy meters, AMI establishes a robust two-way communication network. It acts as the edge data source, continuously streaming real-time consumption metrics. This massive influx of edge data flows upwards into the distribution management system, or DMS, which serves as the local control layer. By processing MI data, the DMS dynamically optimizes voltage levels, isolates faults, and balances local loads, ensuring peak distribution network performance. Moving up the architecture, we reach the critical upper layers of the smart grid, the Energy Management System or EMS, and the Digital Twin Platform. The EMS acts as the central brain of the transmission network, monitoring large scale grid stability and balancing regional load demands in real time. Alongside the EMS, modern grids use digital twin technology. This creates an exact data driven virtual representation that perfectly mirrors a physical substation. This virtual replica provides a risk free environment for testing what if scenarios, allowing engineers to simulate faults without jeopardizing the live grid. By combining EMS oversight with digital twin simulations, utilities can achieve advanced predictive maintenance and unparalleled grid reliability. As we transition to the modern digital grid, we need a universal language for substation automation. That global standard is IEC 61850. Historically, utilities struggled with proprietary protocols, meaning devices from different manufacturers could not easily communicate. This created severe vendor lock in. IEC 61850 fundamentally changes this paradigm. By standardizing data models and communication interfaces, it ensures true interoperability. Now, an intelligent electronic device from one vendor can seamlessly share critical data with equipment from another. This standardized approach breaks down vendor silos, reduces costs, and forms the foundation for high speed queues messaging. In modern substation automation, IEC 61850 introduces a revolutionary protocol, Goose, or Generic Object Oriented Substation Event. Traditionally, intelligent electronic devices, or IEDs, relied on complex hardwired copper interlocks to communicate status changes. Goose transforms this architecture by replacing physical copper cables with digital messages, transmitted directly over the substation's Ethernet network. Operating as a high priority multicast mechanism, a single IED can instantly publish a Goose message while multiple subscribing IEDs receive it simultaneously. This peer to peer digital communication bypasses central routing. It ensures that critical protection commands are delivered with under 4 milliseconds latency. When a power grid fault occurs, the resulting energy surge can cause catastrophic damage instantly. This makes the performance of Goose messaging a non negotiable safety factor. The standard strictly mandates a maximum communication latency of under 4 milliseconds for protection tripping. To put that into perspective, 4 milliseconds is less than a tenth of the time it takes for a human eye to blink. In this microscopic window, the system must detect the anomaly, transmit the digital message, and trigger the circuit breaker. Speed is absolute. In traditional substations, current transformers and voltage transformers, CTs and VTs, output continuous analog signals representing high voltage grid conditions. To bring these measurements into the digital era, we use the sampled values protocol. This process begins at the merging unit. The merging unit rapidly samples the continuous analog sine wave thousands of times per second, converting physical measurements into discrete digital data points. These high-speed digitized CT and VT samples are published as SV streams, replacing heavy copper wiring with precise fiber optic communications. Historically, substations relied on extensive heavy copper wiring to carry analog signals from transformers into the control room. This traditional approach demanded massive cable trenches, driving up installation costs and space requirements. Furthermore, bringing high energy paths directly to operator panels posed significant safety risks. By transitioning to the sample values protocol, these complex copper bundles are replaced by a single, lightweight fiber optic cable. This digital shift drastically reduces material costs and footprint. Most crucially, it completely isolates the control room from dangerous high voltages, fundamentally enhancing operational safety. While IEC 61850 handles high speed communication inside the substation, we need different protocols to transmit data over wide area networks to the master control center. This is where supervisory control and data acquisition or SCADA protocols come into play, managing telemetry and remote control across long distances. Globally, SCADA protocol adoption is highly regional. In North America, DNP3 is the dominant standard, known for its robust data model. Conversely, across Europe, the IEC 608705104 standard is prevalent. Both protocols provide essential situational awareness for grid operators. We also still encounter legacy protocols like Modbus, though modern grids are rapidly upgrading to these secure regional standards. Let's compare the two dominant SCADA protocols. DMP3 is the primary standard in North America, while IEC 608705104 is widely adopted across Europe. DMP3 uses an object-oriented addressing model. It is highly robust, relying on polling and report by exception mechanisms to guarantee data delivery over unreliable links. Conversely, IEC 104 utilizes an ASD-based structure. It was designed to be Ethernet ready from the start, streamlining data transmission for high-speed digital architectures. Despite these structural differences, both protocols have evolved to run seamlessly over TCP/IP, enabling secure, wide area network communications for modern grid operations. While modern protocols are becoming the standard, many power grids still rely on a widely used legacy protocol known as Modbus. Modbus operates on a simple master slave architecture. It is incredibly easy to implement and remains ubiquitous across older industrial systems. However, this simplicity is its greatest weakness. Modbus was designed long before modern cybersecurity was a concern. It inherently lacks critical security features. There is no built-in authentication and no data encryption. This makes it a prime target for cyber attacks. With the shift to modern digital communication, robust security is paramount. Enter NARC CIP, the North American Electric Reliability Corporation Critical Infrastructure Protection Standards, encompassing mandatory cybersecurity standards from CIP 002 to CIP 014. This framework is specifically designed to secure bulk electric systems. At the peak of this framework is the ultimate goal: absolute grid reliability. To achieve this, the standards establish foundational layers of defense, including personnel training, physical security, and electronic security perimeters. These standards are not optional. Non-compliance can lead to massive financial penalties, and more importantly, exposes the grid to cyber threats causing catastrophic instability. To comply with NERC CIP regulations, utility operators must address multiple distinct security domains ranging from CIP 002 to CIP 014. The foundation begins with CIP 002, which mandates the rigorous categorization and identification of bulk electric system cyber assets. You cannot protect what you cannot see. Moving outwards, CIP 005 establishes electronic security perimeters. This requires deploying firewalls and secure access points to isolate critical networks from untrusted external traffic. Beyond digital defenses, CIP 014 enforces strict physical security measures for substations and control centers, ensuring physical barriers and surveillance are in place. Together with personnel vetting and incident response protocols, these mandatory standards create a comprehensive defense in depth strategy for our bulk electric systems. Historically, grid networks relied on a castle and moat security model. Once a user or device bypassed the outer perimeter firewall, they were largely trusted inside the network. However, in modern operational technology environments, this approach is highly vulnerable. If an attacker compromises a corporate IT terminal, they could move laterally to access critical PLCs and IEDs. To combat this, the modern digital grid is adopting a zero trust architecture. The core principle is simple: never trust, always verify. Under zero trust, there is no inherent trust based on network location. Every single connection attempt must pass an authentication barrier before accessing critical infrastructure. As we transition to zero trust, we must address the vulnerabilities inherent in standard operational protocols. This is where the IEC 62351 standard becomes critical. Historically, protocols like IEEC 61850 and DNP3 were designed for reliability and speed, not security. They transmitted data in plain text, leaving systems exposed to interception. IEC 62351 solves this by directly embedding security into the protocol layer. It effectively wraps the standard data packets in a robust cryptographic shield by enforcing strict authentication, digital signatures, and TLS encryption. It guarantees data integrity and authenticity. This prevents man in the middle attacks and unauthorized command injections, ensuring that only verified instructions reach our critical grid assets. To realize zero trust architecture, we apply microsegmentation across our OT and IT networks. Traditionally, once attackers breach the perimeter, they could easily move laterally across the grid. Microsegmentation solves this by dividing the network into small, strictly isolated zones based on function. For example, corporate IT, substation monitoring, and critical protection systems are placed in separate enclaves. Strict security gateways and firewalls act as mandatory checkpoints between every single zone. If the corporate IT segment is compromised by malware, the threat is instantly contained. The attacker is blocked from moving laterally, ensuring a breach cannot cascade into a failure of critical infrastructure. We have now explored the complete life cycle of securing and automating the modern digital grid. Let's synthesize these concepts into a single cohesive picture. Our foundation is the smart grid architecture, integrating AMI, DMS, EMS, and digital twin platforms to provide comprehensive system visibility. At the substation level, IEC 61850 drives digital automation. Goose messaging ensures under 4 millisecond latency for protection tripping, and sampled values replace legacy copper wiring. Externally, SCADA protocols like DNP3 and IE 608705104 reliably bridge the gap between remote sites and central control rooms. Finally, this entire ecosystem is protected by mandatory NERC-CIP standards, zero trust architecture, and IEE 62351 security for strict network microsegmentation. Together, these elements guarantee that our grid automation is not only highly efficient but rigorously secure. Let's test your understanding of the modern digital grid with a quick knowledge check. Question 1. In IEC 61850 communication, what is the maximum latency required for goose messaging during protection tripping? The answer is under 4 milliseconds, ensuring faults are isolated instantly to prevent equipment damage. Question 2. Which specific security standard is implemented alongside zero trust architecture to secure OT network protocols? The answer is IEC 62351, providing crucial encryption and authentication. Finally, which mandatory regulatory framework dictates cybersecurity standards for bulk electric systems? The answer is near CIP, specifically CIP 002 through CIP 014. Thank you for completing this module on digital grid automation and security. Stay vigilant and stay secure.